and unmute. We're here now.
Amazing. Wonderful.
Now the question is, how many people got afraid?
Oh, no, I need to mute this.
Oh, you,
Okay.
you need to mute the stream.
Like 10 different ways I'm joined to the stream right now in our hilarious, weird setup.
So now, before we actually start the recording and everything, we got to do the equipment check for chat's from chat's point of view. Do you see both of us? You should. Otherwise, I've done something wrong. Do you hear both of us? And are the volumes roughly the same?
I guess I could talk to help you clarify whether or not the volumes are roughly the same. My voice naturally varies wildly over time. So
how about we
control is not
alternate between we say the letters of the alphabet, but we alternate between us who says each letter.
Sure,
this feels like a perfect test with no problems.
Can you say it in your native language, and then I'll say it in I guess
I'll try. Yeah, sure.
Okay, you go first.
Okay. A.
B. I said it in Spanish.
Nice. We nailed it on the first try. All right, let's try it one more time. One more time. A.
B.
C.
D.
E.
F.
G.
H.
E.
J.
K. M.
Wait, M. Is L in there somewhere?
I think we missed L. I don't know which of us.
I should have said L.
Well, we've said enough letters now.
Okay.
John is louder. Okay, then I will make you louder. How about now? Let's do the same test again.
Okay.
But this time
I'll go first.
You go first.
All right. A.
B.
C.
D.
E.
F.
G.
H.
I.
J.
K.
L.
M.
N.
O.
P.
Q.
Okay, how's chat reacting now? Chat thinks it's better. All right, then let's give you a slightly more of a boost, and then I think we're good. Okay, and then I will test one more thing. Letters sound more prepared too. It's almost like we practiced. Let's now also see if I do this. You should now see part of my screen and both our faces. If you can confirm that that's the case. You should also see that, Ben.
I left the live stream because it was too weird to see you on a delay and hear you.
I understand.
In the future.
That's fine. But then in theory, chat should see both of our faces on the left, and then they should see my partially shared browser window on the right. Amazing. Okay, then we'll go back to just our faces because that's all we need right now. And then, Ben, I think we're ready. I think we're ready. We can kick this off without any further ado.
There's been a lot of ado so far.
There has been a lot of adoos, but now there are
mostly
no more
ado, to be clear.
There's no more adoos. Cool. Then I will start the recording. Boom. We are now recording. Hi, Ben. Welcome back to another I guess, Rustacean Station marathon. Is that what
we've been calling this year in Rust?
I feel like maybe extravaganza is the right word.
Really, yeah. The problem is that the Rust contributors, they're too prolific. They're just too productive. They come out with releases too fast. If it would really help me if they just stop developing the language. Really, because then we could
totally agree. Totally.
Once every 6 weeks, they're mad. They're crazy.
Yeah.
Who does this? Java comes out once every 6 months, and that's a rush for them. It used to be once every year or two. So
yeah, I think the question really is why are there any more Rust releases at all? They should really just stop. We're done, right?
Right?
The language had its 1.0.
That's the last number. It's think about all the Rust crates you've used. They're all 0 point something.
It's
right?
True.
And so once you get to 1.0, you're washed. So now, you're an old man. The future is now.
The other thing that I'm a little worried about is the fact that we do these every as often as we can, which has become more and more or less and less frequently. But it also means that someone has to edit this whole thing together into some kind of coherent sequence of podcast episodes, which I feel badly for them for.
Yeah, I think, the reason that I'm in this lovely booth is that I was trying to get a nice recording place so people can actually listen to this without having their eardrums explode. But getting the booth is somewhat of a fraught proposition, and so it takes me a while to actually schedule these. And so, in fact, today we're operating for much less time than I thought. Instead of a 5-hour stream, it'd be a 2-hour stream. because I'm getting kicked out in 2 hours.
Well, we'll do what we can. I
We'll
think
do
the
what we
other thing I
can.
can do. Let me see if I can do anything about your. Some people are saying your audio is a little too loud. I've adjusted that now. How about if I do this and this and this? How do we feel about Ben's audio now?
And testing. A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P.
I think that should be a lot better. How does chat feel about this? I guess we'll have you say a sentence. You can literally say a sentence if you want.
A sentence if you want.
Beautiful. Everyone thinks it's better. Everyone's happy, and everyone is still here, which means they haven't run away. What if I turn
Lovely.
this off too? Is that even better? You do have to say something for this to
Oh, I
work.
do. I guess, yeah, sure. I was lost in thought. Hello. Welcome to our podcast, Rustacean Station. I guess I should not do a silly voice if I'm trying to talk normally and do an audio check, huh?
No, it's true. The more normal you can, in fact, speak the most normal you ever have in your life.
The most normal I ever had in my life. Hello. I guess okay, I can't do a bit while I'm trying to actually sound normal. Hi, I'm Ben. I'm being normal right now. I'm not being silly. I'm not being strange. I'm not tapping my notebook to make, ambient noise to ruin the mic check.
That's amazing. I think the crowd is going wild about
Oh, I love
how good the quality of your audio is now compared to before.
Make sure you leave all this in the actual podcast so that it just, annoys people who are listening to it, not live.
Yeah, and then we actually after the fact we post process so that your voice is worse for the people not watching live.
just bit crush my stream.
Yep.
Perfect.
We have to penalize them for not being here in the
That's
moment.
True. Yeah.
Okay, I think then it's time for us to dive into 181.
Right.
And
Let's
the
dive
the first big thing in 181 is that we now have the error trait, Ben. Wait,
It's a huge thing.
I'm confused.
I think
confused.
to help ground us in time, let's say the date of this was September 5th, 2024, right? And so this is not necessarily, if listening to it now in the present as opposed to in the past, violating causality, this is a relatively old release at this point, but it's actually a really huge thing to have core error, or yeah, as opposed to only stood error. Really, we could have an entire podcast just about like the trials and tribulations of trying
this
to
has
move.
been a long journey to get error into core.
Yeah, I believe it was Jane Lisby and her sort of like error working group that had a bunch of ideas for how to improve. I think she's one of the authors of EYRE, EYRE. I could be wrong about that. But one of
Is it pronounced ire or air?
Air?
Like Jane.
No, it might be like Irish. I'm not sure. So I don't know. But the point is that the team worked long and hard on a lot of different error things. This was kind of like one of the culminating things of like finally we can get the error trait into core. And I'm not even sure if I'm like prepared to elaborate on this. We should just interview Jane at some point and be like, hey, like tell us about like what this is, what you've done, and what's left to do, because there's always more to do. Like as long as people are still like turning two crates like this error or anyhow, it means that there's more to do in terms of like uplifting things into stood or like making things easier somehow.
Yeah, I think part of the struggle here, if I remember correctly, was that in order to get the error trait into core, they also wanted to get back traces into the error trait, right? So the error trait is supposed to express errors, which includes the trace back in your source code of where that error originated. The challenge is that backtraces are not a thing in core. Backtraces are only in stood. And so how do you get a trait into core that includes a type that isn't in core? And so
Monumental
a lot of this was figuring out exactly how this should work.
And I'm unclear what actually their final solution, like, in terms of like, there were like a bunch of proposals, and like it was about like trying to find ways to like generically dispatch on like the presence of like whether or not something was like implemented for a type. And there were some wacky proposals that I think eventually did not get implemented. I remember like looking at some of these, be like, what the heck is going on with this? But I don't know. Those would be fun to look into, just because like by reading some of the error in core proposals for how to make all the backtrace stuff work, just like it was doing things that I didn't even realize was possible in Rust.
Yeah.
in terms of
Yeah,
like
there's some
trait
really neat stuff. I
madness.
think what they landed on was where they started was sort of any type downcasting, similar to what you have in I think anyhow prevents
Which,
gives you this,
yes,
which is like you can have a type of error and you can call downcast and you can downcast to any other error type deeper down, which might reveal like for example, imagine you got a an error out of hyper, you could downcast it to an HTTP status code because that was something that was present in one of the stacks of the error. And so they tried to like standardize a generic version of to do that for any type. And I think what they landed on was something that's very highly specific to error. So you can
um,
it's not
possibly.
like a general purpose mechanism for like anything in Rust to downcast to like optionally downcast to anything to carry arbitrary context with it.
It was such a long, like, a long process with so many proposals and so much back and forth that I haven't followed it. I'm not sure actually what they ended up on. I'm just happy that it's here, and I know that a lot of people maybe they're not using core, maybe they only do stood stuff, right? But I mean, people who do use core, I think both you and I, John, we do like no stood stuff for our jobs. It's nice to have things in core. Very often, it's like be like, oh, I want to use the right trait. Oh, it's in stood, not in core, etc. That kind of thing.
Yeah. Yeah. It's also it makes the language feel more complete when you can use more of the language in settings where either maybe you think you couldn't or not feeling like you're operating with like a subset of like some constrained subset of the language for things that
Well,
feel like they should be available
yeah,
just
you
because
kind of
you're
like
using core.
you are using a constrained subset of the language, which is kind of
True.
the whole point. But it's nice to not feel overly constrained. It's like there should be a reason for it, and not kind of just like historical. This whole like core stood split is somewhat unfortunate. In the long term, I keep saying this. Like I'd love the idea that imagine you had a cargo.toml and you just like say stood default features equals false, and you opt into what you need, right? And so you would like opt into Alec or opt into there's all kinds of things. You could opt into like full Unicode support being like up by default. So you wouldn't need to add like 50 megs to like every Rust binary, but only like certain ones that need like full graphene cluster stuff. Or you could have like floating point like turned off for like the Linux folks. You could have so many profiles. And like right
Yeah, it's
now our
true.
kind of like core Alex stood split is like very coarse grained, kind of hacky. It would be so nice to just have like a feature aware stood. And hopefully that's coming. I know there's some kind of like the
Yeah,
build
there's a
stood
cargo
stuff
like
is
nightly
proceeding
feature
this
called
year.
build stood or something that like build stood from source each time rather than using
Hmm.
the like vendored copy that has everything in it. And I think that's like the path you have to take. But then of course now you have to wait for stood to build and there's a
And
whole
that's unstable, so you have to use nightly.
yeah. Yeah, there's a whole bunch of stuff to figure out, but it would be cool.
Here in the modern day, here in the future, that is like, I guess like one of the main project goals for this year is proceeding with build stood to
Yeah.
get it to be in a better place. Um, I'm not sure how about my proposal for feature aware stood. I mean, people know about it. I'm not sure if it's on the roadmap right now, but
You're
I'd
not
love
actively
that.
on the soapbox.
I might be. I'm really like tempted to like start up like a sort of like a shadow libs API team just to like push more things into stood. I'm like increasingly radicalized into like standard lib maximalism over
I
time.
see. I see.
I don't know. So well,
That's
that's a different topic
maybe we'll
entirely.
just get a Ben stood that's a
Hmm.
crate, but it's actually a full standard library.
Yeah,
That'd be pretty neat.
maybe.
All right. Next thing in 181 is a new sort implementation. And this one I did a little bit of digging into because I thought it was super interesting that like we replace them because sorting implementations not very often we get things that are just like all actually better like universally. And it seems like there are two new sort implementations that we got from like a pretty elaborate PR that included a bunch of underlying research as well. And we ended up using something called drift sort for sort and IPN sort for sort unstable, both of which are designed specifically for Rust. I'll link the pull request in the show notes and in chat here. And I think what was interesting to me here is that it's not just faster in terms of runtime for sort, but it's also faster for compile time. So it ends up generating less code to compile, and given sort appears in all sorts of places, that ends up having an actual effect. That's pretty neat. And then it also has this side property that it validates the implementation of the ord trait. So if you have someone that implements ord incorrectly, like non-deterministically, for example, then you would end up with a panic come, or I forget what there's I think it's a panic that comes out of this new sort implementation in debug mode that tells you you have a non-deterministic implementation of ORD. There's no guarantee that your things will actually be sorted, and this is like not intended to be done, which I thought was pretty neat.
Yeah, that too, I think, is worth like a deep dive. Like if somebody out there wants to interview the author and just send us an audio file, because just like learning about how they did that, like detecting broken order implementations at runtime while still managing to be faster and compile faster, is pretty neat. I'm not sure who came up with this sort implementation, or if it's like from like a well-known paper or something.
No, I think
Um,
they actually did the research specifically
Amazing.
for Rust here. And their username is Voltifer, Lucas Bergdahl, and Orson Peters seem to be the two people who have designed and implemented. And there's a whole long like paper and lots of experimentation they did for both of these implementations. So it's pretty neat.
Let's keep it moving along here. So the next topic up here is the expect lint. Okay, and so this is actually a pretty cool thing. If you aren't using this, maybe you should be. And so you're probably aware, if you use Rust, that Rust likes to give you warnings about certain things, and then Clippy especially also likes to give you warnings. Kind of all it does, really. And then so, but what if Clippy gives you a warning that you want in most places, but not in this one place? Or what if you have Rust? Same thing for Rust. Like maybe you really don't care like for this one type, something like bad style, whatever it's called these days, wrong capitalization, right? And so normally you would slap on an allow attribute and say allow the lint in this one case or for the entire module or whatever the scope is for normally. The thing is that if the thing that triggers the lint ever goes away, you just have kind of this allow here sitting there uselessly, and maybe it's a problem if it goes away. Maybe if like you expect there to be foreshadowing, some kind of warning that arises. And if it doesn't arise, maybe you want to know about that and want to have it say, hey, the compiler to say, hey, like something's off here. And so now there is a new, as opposed to just having allow, forbid, deny, etc. There's a new expect new, right? A year ago, expect lint level, all right? And so, or attribute, say, for the linting machinery that lets you say, hash expect and the name of the lint. And then if it acts like allow, where it's like, hey, like I know this is going to happen, don't warn me about this. But if it ever goes away, if the lint ever stops happening, it gives you an error. And so just like if you're using allow, maybe you should just be using expect everywhere. I'm not sure there's like much reason to use allow over expect at this point, frankly. Do you know any, John?
No, I mean I think I've seen it in a couple of places where people want to maintain backwards compatibility with older versions of Rust, and so they need to write code in such a way that like would trigger a lint. But when they eventually bump their minimum supported Rust version, then they want to like remember to remove the need for that. But for now, they expect that like a macro, for example, generates something that induces a warning. So it can be that kind of stuff.
Mm-hmm.
But I think for a lot of use cases here, this is more of a you want to make sure that you don't allow lints that you could now remove. You only want
Mm-hmm.
to like allow yeah, I'm not sure what like the compelling use case here is beyond just trying to like keep some hygiene in your code, right?
Well,
Like
it's the same thing with like imagine Rust warns on unused imports, and like in reality, like what's the harm in an unused import? It's only I guess for a trait could like collide, but and otherwise just an import, right? And so, but with Rust warns you on that because it's kind of like like, you shouldn't have clutter in your code that isn't there that you aren't using, right? And if like you have this allow trait. And like it's not actually like triggering on anything, and you actually don't want it anymore. It's become vestigial. Well, how would you ever know? And so the expect is kind of like that, where it's like, hey, like well, an unused import is getting as a warning, and I expected this trait or this warning to happen, and it doesn't. And so you can erase me.
I see.
I think it's
So
just
the argument would almost be anywhere where you currently use allow, you should replace it with expect.
that's what I'm thinking. Yeah.
Yeah. Yeah, I could buy that, and I think it will probably be more likely to be used for Clippy lints than for Rust C lints, right? Because Rust C lints tend to have fairly few false positives.
They tend to be fairly a higher bar. Yeah.
Yeah,
So.
whereas the Clippy ones, like there are some that have known bugs and whatnot, and so you do have to allow them sometimes, and then you would want to know when Clippy has gotten smart enough that you can now get rid of the allow. Or then the expect. This relates nicely to the next thing that was in 181, which was lint
Please
reasons.
feel free.
So lint reasons are basically they add the ability for you to say, allow this lint or deny this lint or expect this lint, comma, reason equals, and then a string. And the thinking here is that if you want to allow a particular lint or you want to deny a particular lint, you should ideally tell the reader of the code why that's necessary. For deny, that might be something like we deny the use of unsafe code, but it could also be something like we've been bitten by code that uses this particular pattern in so many cases, and so we're actually going to deny a Clippy lint that is experimental or pedantic because specifically it matters a lot in this code base. And so that might be the reason you give, so that someone doesn't remove it just because they're like, this doesn't trigger anything anyway. And then I think you could also use it for allow lints if there's some code you've written where maybe it's a Clippy safety lint where it sort of says this code is like error prone to write in this way, but maybe you're at the assembly level and you know that it has to be written exactly this way for the optimizer to generate the assembly that you want. Then you can put in allow this lint here because the code has to be written in exactly this way because the assembly needs to be stable or something like that. So that's where lint reasons might be useful. And in general, I would expect people to use them in 50% of places where they declare a lint. Seems about right to me. Like usually when you declare a lint, you should probably say why it's necessary to explicitly annotate that lint, either for allow or deny. I think that brings us on to stabilized APIs. Is there anything that particularly stuck out to you here?
I mean, aside from core error, which we've already gone over, hold on. What is hint assert unchecked? It seems like we already have.
I thought
I see.
duration
cool.
absolute diff is one I've definitely wanted in the past, where I have
diff.
two durations and I want to. I have two. Is it for durations or is it for instance?
It's for
so it
durations.
takes two durations and it gives you the difference between them in absolute terms. So like the time that elapsed between them, but without you having to check which of them is earlier, or which of them is greater or smaller. Because durations in the Rust standard library cannot be negative. They can only ever be positive. So if you have, let's say, a duration of 1 hour and a duration of 2 hours, you have to do the 2-hour one minus the 1 hour one. If you did them the other way around, it would basically panic and then be like, hey, durations can't be negative. Whereas with absdiff, you could do them in either order and you would get a diff of 1 hour.
I think hint assert unchecked is pretty interesting, and so like a lot of obviously unsafe, as hopefully the name suggests. Anytime you see the unchecked thing somewhere in the standard library, you should assume it is an unsafe function that is has some kind of soundness precondition, some invariant you need to uphold. And so this is in the hint module, and so the idea here is that, like many of the unchecked things, this just let you assert to the compiler. All of these unchecked things are assertions. This one is actually called assert unchecked. That something is true. Some property holds, which can allow the optimizer to see through certain things or to prove certain things about your code, which allows it to generate faster code.
Yeah, the one thing to be really careful about here, though, is that assert unchecked is unsafe. And it's specifically unsafe because if you ever pass false to that function, you trigger undefined behavior. So assert unchecked is not a check if this assertion holds.
Yes.
It is I promise that this assertion holds. And the distinction is pretty important compared to the standard assert macro.
I wouldn't even say that. And so it's a different, it's how you think about the idea of an assert in language and programming in general. Like no matter what, when you assert something, the program will not continue past that point. Normally, right, like an assert in Rust or in C, right? The idea is that the program will uphold this invariant or crash, right? Either this is true for all following things. The unchecked part is just that this doesn't crash, but it's still like your valid program is only valid if this is true. And so assert in any case is a way of upholding some kind of invariant in your program.
And I think just because it might be useful, like why use assert unchecked rather than just using assert if assert is like safer and aborts your program?
Because sometimes you don't want the panic machinery to be linked into your program. Sometimes, again, it's mostly for performance. Again, I would encourage you to never use this function unless you have benchmarked it and you said, hey, I'm in a hot loop and Rust is failing to optimize out the panic branch, or the code size is causing it to not inline it when it should. And if you haven't benchmarked, don't use unsafe code, right? Or at least not, as FFI code, which is unsafe for that reason. And then there's like, Rust unsafe, which is like, if you haven't benchmarked, don't use it. Rust is pretty good. Uh, you should benchmark, and sometimes you do need to use it naturally. But other than that, just use assert. But for the times that you need it, like I think it's pretty cool to kind of like peel back the layers and like understand, hey, this is how the optimizer works. It just it knows things about your code, and then it optimizes accordingly. And asserts are just ways to hint, like
Yeah, it's like
express information.
give additional information to the optimizer.
Yeah, if you think about like programming languages with both types and like compilers as like proving systems, like mathematical sort of systems, like an assertion is like an axiom. It says like this is true, right? And so if you want to have a sound and coherent program, you actually need those to be true. You can't
Yep.
assert false. You can't assert that true is false, which that's a classic example of a completely insane mathematical system.
Yep. I think the other thing that was interesting here, which also shows up in the compatibility notes further down for 181, is that there's a change to the arguments for the panic handlers. So there's now a panic info and a panic hook info, and those are now two different types. And one of them is the argument that you get to the panic hook that you can set globally in your program, like the thing that gets called if a panic ever happens. And then the other one, panic info, is the one that gets passed to the thing that the function you've annotated with the panic handler attribute, like hash square bracket panic handler in no-stud crates. And these are different because in no-stud, what you get in a panic is always a message, like a string. Whereas when you have the standard library, the thing that you send to a panic can be an arbitrary type. So you can use panic any, for example, and given any arbitrary type, the thing gets propagated up through panic hook info and ultimately passed to the panic hook handler. But these two are different. Like the one in core is more constrained than the one in stud. And so these two types had to be split, where previously they were the same type. And so this was like, I think the old name that they've sort of continued to use, but it's a type alias, and then eventually they'll deprecate it, and then eventually they'll remove it fully. So I think technically this is a breaking change, I believe. Or actually it might not be, because in the versions where the old one exists, I think they only had methods that will be provided by both. And so eventually the panic hook info one will gain additional capabilities that the panic info one did not and could not get because it had to support core as well. So I thought that was an interesting way to sort of evolve the panic hook infrastructure here.
Also, one more API is the fs : exists, so the file system module now gain the ability to check to see if a file exists without having to first like construct a path and then like see if use the path : exists method.
Yeah, because that one we've had for ages, but fs exists we have not as sort of a freestanding function.
Slightly more convenient.
Yeah. There's
Go
another
on.
compatibility note here around panicking through extern C, and I believe we talked briefly about the C unwind extern in a past episode. Do you remember the context here, Ben?
Right. Yeah. So we just talking about panics and like panic hooks and panic payloads. Why does Rust let you catch panics? For a long time, it did not let you catch panics in any sort of reasonable way. Why was this feature added? Like, what's the goal? I know people kind of like lots of people, either it seems like most people either ignore panics, they're fine with it, or they kind of like don't like, they're like, panics, like gross, right? And so it's always a sentiment of like maybe Rust shouldn't have had panics or let you catch panics. And the reason that Rust does is because if a Rust component is a host in some larger process and the Rust component crashes, sometimes you do not want the Rust component to take down or the larger process, or sometimes you just cannot are not allowed to unwind out of that Rust component. One example of that being that unwinding across language boundaries is largely undefined behavior, especially into C, like maybe not into C++, depending on the platform and ABI. But in C, it definitely is undefined behavior because C doesn't really have unwinding. And so if you had a Rust library linked into a C library and the Rust library panics and tries to unwind it to C, it's just nonsense. And so the best practice, what you should have been doing all this time was if you have any sort of Rust library that exposes a C interface at every single entry point, every single extern C function might be getting called from a C component, you should be catching any potential panics or otherwise proving that panics can't exist, which is kind of tricky, right? Uh, and so that's kind of a pain. And because it's kind of like, well, this is just boilerplate. When is it ever useful to like, force people to actually do this stuff, which they often forget to? And so the alternative is that what if we just said, hey, we control the code gen for all these extern C functions. We could just say that if we ever encounter a panic in any of these, it just aborts immediately, right? And so the problem is that's a behavioral change, and so it requires some care. And so they introduced a new ABI, as we can see in 1.71, 10 releases before this one. Or it was actually, which one is this? Oh yeah, it's 81. And so there was a new ABI called C unwind, and we talked about that back then probably, where the idea being that one of these ABIs, extern C, works as it has historically, and you probably should be careful and maybe not use it. And the other one is the actual, C unwind is the one that doesn't abort on unwind, as far as I understand. So programs relying on unwinding should transition to using the -unwind suffixed ABI. And then the basic normal extern C ABI has now had a behavioral change where it will abort on panic, which is technically a breaking change, but really what you should have been doing anyway. I don't think it's been any problems. One of the great things about being a year behind is that we can see in retrospect
how
whether
things
or
panned out.
not there were actually like any like big commotions over
Yeah.
any of these like minor breaking changes. And it turns out in this case, probably not. You shouldn't be panicking in any Rust code in the first place, ideally, and then you definitely
Yeah,
should
it's
be
like
doing
your
it across the
program
prime
was
boundaries.
wrong if you weren't catching the panics in the under the extern C in the first place anyway.
And maybe you were, but in that case, like the most that you could be doing is kind of just like returning some error code to the C program and then like continuing on in kind of like a degraded state. Which is also itself kind of questionable, but not necessarily unwarranted, which is why the C unwind ABI still exists. And so it's a correctness bug, first and foremost, that just happens to allow you to opt into loosey or goosey or semantics if you really need it.
There's also, I guess, this is somewhat related, right? So this is not about externs, but about targets. So the WASM32 WASI target, which targeted WASI 0.1, is now going to start issuing a compiler warning, and then down the line, it will eventually be removed. I think this was because WASI 0.2 was stabilized, and so they don't want WASM32 WASI to refer to the old one and then to have uses of newer standards and eventually at 1.0 to not be the one you get when you use the most obvious name.
This is let's have some background here, right? So WASM is the bytecode format that originated for web browsers based on ASM.js, where the idea was, hey, let's just have like a generic sort of bytecode format that we could, ship to JavaScript runtimes and like run in a sandbox and do all the fun stuff that like Java thought it was going to do back in the 90s before like security was discovered. I mean, I'm not wrong. And then WASM is fairly limited. It's mostly kind of just like browser stuff and doesn't actually have like platform things like detect for like file system, etc. And so WASI, W-A-S-I, is the system interface for WASM. The idea being that it's kind of the libc equivalent where it gives you files, it gives you network sockets, etc. Right? And it's been a long time coming. They're doing a lot of good work. A lot of former and or part-time Rust contributors, so like Alex Crichton and Dan Goman. Brilliant guys. Dan has like open office hours, I believe, every so often. We're just like to go pick his brain about like things. And like, if I had to levy criticism, it's that they really care about doing it right. They kind of feel like this is the last chance anyone's ever going to have to like, really introduce a platform that like does the right thing as opposed to just like being libc again and repeating all the same mistakes.
And they might not be entirely wrong, at least for a pretty long time.
But it is taking a long time because they want to do it correct. They want to have like capabilities, which is like, oh, I love capabilities. Oh my God. This actually works out. It would be like, save me from Unix.
Yeah.
But in the meantime, it's taking forever. And so, one of the problems with Rust being an early adopter of WASM is that we kind of just like, yeah, sure, they could be WASM 1.0. Let's just call it WASM 32.WASI. There would never be any problem with this. And then like WASM 0.2 came out, and I think pretty soon WASM 0.3 is coming out.
Yeah, I think so.
On a much faster schedule than 0.2.
I think they're changing the naming scheme now to be WASM 32-WASI P and then a number for P for point, right? So point 0.1, 0.2, 0.3.
Which is like, doesn't as long as the WASM32-WASI is open, as you were saying, for the eventual 1.0 release, eventual, right? Uh, then that's really all that matters. It doesn't matter if
Yep.
there's like some inconsistency of the naming scheme, because ideally, in the long term, people won't be using
Yeah, and
the
I
point
don't think I
releases.
heard of any like major breakage as a result of this either, because I think there was a long enough period of warning people, and the change was straightforward enough. But it was just like a slow rollout of we're deprecating this name, and we will eventually remove it.
Hmm. Right,
And then I think the last bit that's in 181 is a fix for a CVE around escaping arguments when invoking batch files on Windows in the presence of trailing whitespace or periods. This one is very niche, but you can go look at the CVE if you want. This
there's
one
a very good
specifically, I
write up,
think
and there's a
around
blog post you can read from the
yeah,
Rust.
there's a blog
We'll
post
link
for
it in
the
the show notes.
CVE, and there's also like this affected use of the command type in std process, I think, where like if you gave a command a particular name and ran it on Windows, then it might end up doing different things than what you expected, because the way you invoke things using batch on Windows is batch shit crazy. Get it? Batch shit. That was kind of funny. Kind of funny, man. I also looked through the detailed release notes, but actually the main thing I found in there for 181 was the PR for replacing the sort implementations. And so I don't think I have anything else for us to go in there. So we could go move on and be crazy and move on to 182 if you think you're ready.
Let me just say I do encourage everyone to read this blog post about the Windows sort of command injection sort of thing here, because I know like a lot of the discourse around this when it happened, because it's not like a Rust thing. This happened for lots of languages, I believe. It was kind of discovered
Yeah,
this
it
around
was
the
a
same
pretty
time.
big episode.
A lot of people didn't realize that batch file parsing on Windows had this sort of peculiarity.
Yeah.
And so a lot of the discourse was around, oh, Windows is broken, parsing is wrong, etc. Right? But you really, if you're using standard command and any part of the arguments are controlled by outside input, even if you're on Unix, you really need to consider this. Right? This is like, it is about kind of like, SQL injection, right? Nowadays, we know, hey, like you need to prepare your statements and don't just use string concatenation. Be careful about any of the parameters that are controlled by outside forces, right? You need to do the same thing for much more severe cases. It's even more severe, right? If you are spawning a subprocess using arguments taken from user input.
Yep.
And that applies regardless of platform. You should just be careful about this.
Yeah, and if I remember correctly, there's something here around the way that you start processes on Windows requires that you pass in the argument list as a single argument. You don't get a way to like pass it in as multiple arguments the way you do on Linux. It's like it's not an array, it's a string. And so you need to escape the string such that when it gets parsed into the right sequence of arguments rather than incorrectly not representing the array that you passed in. And so I think that's where the problem was lying. And it affected a bunch of languages. Like I think Python was affected too, and Go. This is like a whole internet-wide episode.
But I do want to emphasize, right? And so obviously the Windows having freeform sort of like, parsing, wibbly wobbly parsing and strange historical parsing didn't help things. But it still remains the case that even though the Unix style of like one string per argument, or sorry, an array of separate strings to indicate arguments is more resilient against this kind of thing, it's still vulnerable. You can still get shell injection if you aren't careful. And so be careful. If you're spawning some processes, you need to know about this.
Be careful when invoking anything to any bash is a good advice. All right, I think we're on to 182, released October 17th, 2024. So that's 1 year and
we're almost less than a year behind.
Yeah, it's great. First thing we got in 182 is the cargo info command. This one is actually something I've wanted for a long time. It's just a way to look up information about a crate in your dependencies or a crate not in your dependencies without having to open the browser tab to look at it. So you can run cargo space info space and then the name of a crate, and it will show you a description of it, its current version, what the latest version is, its license, link to its documentation, what features it has, all of that stuff. It will also tell you whether, like, what categories and keywords it's in. And if it is a dependency that you have in your current project, it will tell you what version you are using. And then it will tell you what the latest one is if they differ. So it's just a handy way for you to look up that information without having to look it up online, that has existed as a bunch of external cargo subcommands, but now finally is built in. And this is one thing we see a lot in the cargo ecosystem of people build out external subcommands outside of cargo, and if they prove universally useful enough, then they get brought into cargo itself and supplied as sort of a built-in command, the same way we saw for cargo add, for example. We also have a bunch of Apple Target promotions. Do you have any context for these, Ben?
Well, if you recall, a few years ago, Apple switched from x86 to ARM for all of their things. Actually, it'd be really funny to be like, a few years ago, Apple switched from PPC to x86, as though we were like 20 years behind as opposed to 1 year. But yes, and so the idea being that Apple, okay, so the way that support tiers work in Rust, the Rust compiler has tier 1, tier 2, tier 3, actually it's more than that, but there's details. Where the idea being that every tier of support implies like the higher the tier is, I guess the lower the number, right? The lower the number is, the more strict Rust is about testing and guaranteeing that there are no breaking changes. You might be like, oh, okay, well, ARM Macs aren't that new, right? They're like 2022 or something like that. And so why did it take until 2024 to actually start making this a tier 1 platform? Especially you saw it coming, right? The problem is that Apple hates CI. Apple cannot, you are not legally allowed to virtualize Macs except for like, very Baroque circumstances, and it's very expensive. And so in order to actually get ARM-based Mac CI runners took years. And so just because like Rust uses
and I think it
GitHub
ends up
for
just being like
things and-
server racks of Mac Minis.
Yeah, that's how you do it. Like you can't just have like for like Windows or whatever. You can just have like a server that's running VMware or whatever your software virtualization of choice is. Maybe not VMware these days. And you can be like, yep, I can have like 10,000 Windows VMs on there. And like with Mac, it's like a very strict limit of like you must own Mac hardware. You get like a very small, like maybe like single digit number of like OS installations per hardware piece, and it's just like the biggest pain in the world. And so it took, but finally now 64-bit ARM is now sufficiently supported in CI providers to the point that Rust can begin giving it tier 1 support, where tier 1 means that every single commit to the Rust compiler and also cargo, etc., gets tested against the Mac CI. And so like there is never a point where like, the head, the tip of the branch of Rust is not passing all the tests on every tier 1 platform. And so it's actually a big deal. It's like it costs a lot of money. It takes a lot of time, like in terms of just like waiting for CI. It happens in parallel, right? But like the slowest platform, is a bottleneck on every single thing. And so you have to run the entire test suite, build all the stages of the compiler, actually verify them. And so it's a big deal. And obviously Mac's an important platform, but it is just like it took a while for this to happen because it's just.
And do you remember what tier 2 promises?
Tier 2. Okay, so we can go. If you go to forge.rustlang.org, rust-lang.org, you can see the Rust Forge, right? And they kind of like should have some kind of thing about in the left side, platform support. Look for platform.
Yeah, so I think tier 2 is like it's guaranteed to build, but not necessarily guaranteed that all the tests pass.
That's it, yes. And so they don't run the entire test suite on tier 2 platforms. They just check that it builds, just significantly faster.
Yeah. And then because the macOS on ARM is now tier 1, and then Mac Catalyst targets are now tier 2. Mac Catalyst being like the iOS, one of the iOS targets that allow you to like target iOS but run it on a Mac. That's now tier 2.
Okay.
I think it was tier 3.
The platform support page from the Forge to the Rust C book, and so we'll put a link in the show notes for platform support. I guess we should be doing it probably live in the side chat. But yeah, so doc.rust-lang.org in the Rust C book is an entire book for contributing to Rust C, and there's about platform support describing like there's tier 1 with host tools, tier 1, tier 2 with host tools, tier 2 without host tools. And then tier 3, where tier 3 we haven't talked about yet is just like the compiler contains support for it, but it is not tested.
Yeah,
And
I
there are all
found it.
kinds of like,
I'll put it. I'll put a link in both in chat and in the show notes.
yeah, and so it explains like all the targets, all kind of like, what they all mean. Gives you tables describing, whether or not certain library is built for the more obscure ones, for the lesser tiers. And so if you ever wonder like how many platform press supports, well, tier 1 and tier 2, modest amount, reasonable but modest amount. Tier 3 is a ton of obscure platforms which
Yeah,
you've like probably
tier
never heard
three
of.
is basically like it's. I think it's not checked in CI, right?
It's
It's
not.
just like
No.
there's the Rust scene knows about the targets, but that's all.
hmm It's in theory, Rust should support this. It should, all the feature, all the config flags should support it. And like if there may be custom code in the standard library or the compiler to accommodate this, but it's all community supported.
Yep.
And who knows if it actually works? It's up to you to report that. So
And then the first sort of feature we get in 182 is precise capturing use syntax. Now this one requires a little bit of explanation because you need to know about what lifetime capture is in the first place, and this differs between the 2021 and 2024 editions. It's something we've touched on briefly in a past episode. But the basic idea here is imagine that you have an asynchronous function. And part of its arguments include something that has a lifetime. Like maybe it's an asynchronous method, so it borrows self, or it just takes an argument like a reference to a stir, and that value is carried into the future that you return. This could also be a regular function that returns something that captures a lifetime, but generally this is something that comes up for things that use impl trait in the return type, and where the actual type, the concrete type behind the impl trait, captures some lifetime of the input. And the question becomes, how do you express, like syntactically, this fact? How do you say, function foo takes a stir and returns an impl bar and includes this reference? The traditional way that people have often done it, partially because the compiler was recommending this for a period of time, was that you use like impl bar plus tick underscore to say like, I want to sort of bind the return type here to also mention this lifetime of the input type. If it was a named lifetime, you would do plus tick a, and if it's not, just plus tick underscore and let the compiler figure it out. It turns out this is wrong in like a variety of subtle reasons. And the actual way to capture that you are capturing a particular lifetime in the concrete type includes something called the captures trick, where you need a trait with some bounds, and it gets all pretty messy. You can read more about this, some linked things from the 182 release notes on this topic.
it's a very long section about this. Yeah.
There's a lot to discuss of like how to do it correctly. But the bottom line is that as of 182, we now have a new keyword you can put, use, and use takes a list of type and lifetime parameters. So angle brackets, same angle brackets you would have after impl, for example. And the things you put in that in that use angle, in those use angle brackets, are the things that this impl trait will capture. And so you can list out their lifetimes and you can list out their generic types. And the idea is that this communicates exactly what is being captured. So if you want to capture the lifetime of some input argument, you would put its lifetime in that list. If you want to capture a particular generic of the input, then you would put that in that list. Now, Rust has rules for what it infers by default that you want to capture. And those rules differ in the 2021 and 2024 edition. So in the 2021 edition, Rust implicitly, if you don't write anything else, will assume that impl trait captures all generic parameters and no lifetime parameters. And this is like sometimes what you want, but very often, especially for things like asynchronous functions, what you actually want is for them to capture lifetimes. So the rules in the 2021 edition are actually kind of subtle. For asynchronous function, it will assume that you capture all lifetimes and generic types. But for functions that return impl trait, and remember, async functions are really the kind of sugar for a function that returns impl future. But for async functions specifically, the rule in the 2021 edition is that you also capture the lifetimes. And so this meant that there was this sort of discrepancy in the rules in 2021 between impl trait syntax and async functions. In 2024, this discrepancy is gone. So in 2024, the assumption is that both async functions and impl trait return types capture all of the lifetimes and all of the generic parameters. And the use thing you can put at the end, so plus use angle bracket, allows you to constrict or restrict which generic types and which lifetimes are actually captured by this impl trait. So if you don't want the default of capturing all of them and you want to be more specific, saying it's only this lifetime and these two generic parameters, you can now do so. I believe in this particular version, the use keyword is only usable in the 2024 edition. I think they've opened up the use keyword to the 2021 edition in a later release that we haven't talked about yet. But this is what time travel does to your brain.
Yeah.
But this is like, hopefully explains roughly what use is for and why it is useful and what they kind of had to fix. Like this discrepancy was just weird because it meant that if you took an asynchronous function and turned it into a function that returns impl future, it might no longer compile because it would complain that you're not capturing these lifetimes. And that problem is now gone in the 2024 edition. It's all nicely consistent now.
Yeah, this is one of those things where ideally you would never need to think about this. I think there's a recent blog post from Nico, recent as in like today recent, not recent back when this was released. With the idea being that Rust should give you should have syntax for like, you know, the things it needs to, even if they're kind of like ugly and gross, but ideally should like do the right thing and not require you to use the ultra explicit ugly syntax. And like
Most
only
of
people
the
who
time.
actually need that power. And this is kind of like, I agree, I don't like the syntax very much. I've never needed to use it. And I think the hope is that almost nobody should. I mean, again, in retrospect, I've spoken to some folks since then, and they kind of like have sadly said they do actually need to use it occasionally. And so maybe in the future it can be improved to either be prettier,
Yeah.
less weird
Well,
looking.
so I mean, one of the things that it's useful for is if you have a function that does some work. So imagine you have a function that you returns impl future, and you want it to do some work before it constructs the asynchronous function. And it uses some of the input arguments before constructing the async event. Like, let's imagine it takes a string reference and it turns it into an owned string outside of the async block it returns. And then it moves the string into the async block. Then now that future that you returned is not borrowing the stir. Because it has an owned string, but Rust would infer that the lifetime carries over into the output type. And so that the use syntax would allow you to explicitly annotate that lifetime is not used in the return future, and therefore make callers not have to keep the stir alive. So it actually allows you to build APIs that are more flexible if you choose to use them.
Okay. There's a lot in this release. This is a huge release. I forgot
I know,
how
182
big this release
is
is. You've
is
got to keep going.
enormous. Yeah, let's keep going.
So moving on, native syntax for making a raw pointer, right? And so there's a really, really great blog post series we've recommended all the time on this podcast by Ralph Young about like, you know, what is a pointer? What does it mean to be a pointer? What is the property of a pointer? Like, what do they actually let you do? And how do compilers see pointers and optimize around pointers? And we should link the entire series of blog posts. These like the 3 in the series. But the long-term repercussions of this are to kind of like, you know, nail down. Ralph Young is the leader of the Rust Unsafe Code Guidelines group, or at least I'm not sure if he's the leader. He's like the kind of one of the biggest proponents of it. The idea that Rust should write down what it means to have unsafe code, and you know, have like a rigorous like definition that can be like, you know, deformalized, like type checked, in like a mathematical way. And right now it's kind of like, yeah, just don't do the unsafe stuff, right? It should be much more precise than that. And one of the things here is kind of like, well, what does it mean to be a pointer? Can we like, you know, how do we like convert things to raw pointers and, you know, the interaction between references and raw pointers, right? And for a long time, the idea was, how did you create a raw pointer in Rust? Well, there's a coercion between references and raw pointers, and so you can take a reference to a thing and then just use the as keyword to convert it, or just rely on the coercion to kind of like, yeah, if you need a raw pointer, just like take a reference and then there you go, you have a raw pointer now. Just use it wherever you'd like. The problem is that references have invariance where you must uphold a certain invariance at all times. It's not enough to like use the pointer that's pointing to invalid data to even have a reference, a Rust reference to an invalid sort of type it's unsound. It's a memory safety issue. Your program is wrong. And so, but like, I mean, like, how do I do it? Like, how do I, if I can't use, if I have to be careful about like, okay, well, like, this reference to this value may or may not be like, sound, depending on the value it's actually containing inside of it, right? How do I
I guess
actually
to
use
give
this?
an example here to people who haven't worked with this directly, an example of an invalid reference would be something like a reference to a field of a packed struct where that field is not aligned. So there's a rule in Rust that a reference to a T must have an address that's aligned to the size of T. So if you have a reference to, let's say, U64, then the address must be U64 aligned. So it must be 8-byte aligned. So the sort of bottom 8 bits, if you will, have to, not the bottom 8 bits, but you can't have a pointer to an 8-byte aligned value that doesn't point to a multiple of 8 address, because
Mhm.
addresses point to single bytes.
And that's only one example of like, how
There's
to
only one
create.
example. But
Yeah.
so if you have a packed Rust struct where some of the fields are not aligned, trying to take a reference to one of those fields will not work. The compiler will not let you, because it would be unsound to create such a reference.
Right. And so the idea is, well, we need to create raw pointers sometimes for cinterrupt. How do we do it? If we can't use the reference operator and then cast or coerce to a raw pointer, how do we do it? We just need to have first class support for the reference operator then, or have for some first class way to go from a value to a raw pointer to this value without needing to round trip through a reference first, right? And so the idea was, okay, I'm a big fan of this approach, right? My famous line is, "Read my lips, no new syntaxes." I'm not sure if you understand a George Bush the first reference from 1990, John. But anyway, the point is, right? I don't like syntax in my language. I want everything that can be a macro pretty much to be a macro, with some exceptions, right? I'm a little bit.
So you
A little
got your
bit
wish for this one initially, right?
well, here
Adder
initially,
off.
right? And so, like, I want all new features to begin as macros, and then I want them to graduate to syntax once they have proven that it's actually worth having syntax for a thing. I think the idea of starting like any feature starting as like making new syntax is nonsense. Just use a macro for it, right? And then eventually, like, right, so we did this for async. Originally, we awaits, right? We're just a
Oh
macro.
yeah, I
People are kind of like,
remember.
well, it's
I
much
remember.
nicer to have postfix await than to have to wrap everything in these await macros. And so I'm fine with that, right? The try macro, try began as a macro. It's much nicer to have the question mark operator in the end and have to wrap everything in a try. I'm fine with that, right? And then so this also began as a macro. And so we had the standard pointer adder of and adder of mute macros, which were the first class ways to create raw pointers in Rust. And now we just have this ampersand raw syntax, and I actually use it all the time, right? And so again, maybe kind of niche for some people, but like I do all kinds of cinterrupt for my job, and I use it all the time. I'm fine with it.
And it's
It's
maybe
kind of
worth
like,
pointing out that the adder of macro is another example of a macro that you could not write yourself,
mhm.
because it internally uses unstable features. But it's sort of, the standard library is allowed to use it because the standard library is special. So the standard library is allowed to implement this macro and internally use sort of private unstable features that you could not write yourself.
It's not even unstable features. I'd say the standard library is the interface between, like, where does the language end and the library begin? And there's
Yeah.
plenty of things in Stood that you could write yourself. And there's some things that you could not, just because they are like vaguely language level, like special.
Yeah.
And so like just so like so the standard library in Rust is the kind of glue between like what is the language level and what is the library level. And so in this case, right, that adder of macro was internally using an intrinsic that allowed you to actually create a raw pointer, but like it's just a library level way of writing a language level thing. And so without having to actually stabilize a language level thing, which they did in this case. And so yeah, if you need again, the point is, if you are making a raw pointer in Rust, use ampersand raw const ampersand raw mute, and that's all there is to it.
This next one I'm actually really excited about. So this is we now have unsafe extern. So previously, when you declare FFI functions, you had to declare them as extern C, for example, or ignore the case where you can omit the C and let's say extern C or extern C unwind or whatever it might be, and then a function and then a function signature. And when you declared an extern function this way, an FFI signature this way, that function is unsafe to call. It's always unsafe to call. And the reason it's unsafe to call is a combination of two things. It is, did you get the signature correct? Like, does the signature match the function that's going to be provided on the other side and what it expects the calling convention to be? And then the other part is, because you're calling an FFI function, Rust has no knowledge about what that function might do. It might like overwrite all of memory with zeros, which would violate Rust memory safety. And therefore, like there might be safety invariance of that function that means that it, you know, is unsafe to call for some other reason that the calling convention being wrong or the function signature being wrong. So what's landed in 182 is that now you can declare an extern block itself as unsafe. And it will eventually become, I think, required in the 2024 edition to make the extern block unsafe. The intuition here being, what the Rust folks realized was they were trying to figure out this question of, should the onus of proving that the type or getting the type signature correct and the calling convention correct, should that onus be on the person who writes the extern declarations, or should it be on the person calling the function using the extern? And they were like, it feels like it should be on the people writing the extern, not on the people calling it. But previously, if you just declared it extern, there was nothing unsafe about declaring it extern, but it was unsafe to use it, so the onus was on the user. And so what they've now introduced with this ability to write an unsafe extern block and then extern functions inside is you're making it unsafe to declare that this is the calling convention and signature of this function. And as a result, calling it can now be made safe. So when you have an unsafe extern block, you can now declare each FFI function inside of that block as either unsafe or safe. If you declare it as safe, what you're saying is, I got the calling convention right, I got the function signature right, and this function doesn't do anything wacky to memory safety more broadly, like overwrite all of memory with zero. And so as a result, it is actually safe to call. And that is a huge improvement to the sort of FFI world where you no longer must use unsafe for any FFI call because you can give all the guarantees at the declaration site. Obviously, there will be some functions that have additional unsafety guarantees. Like imagine you have a function that takes in, I don't know, a raw pointer, and it is internally going to dereference that pointer. Well, that function is still going to be unsafe, but the safety requirement of calling that function is now limited to the things that are specific to that function rather than having to do with the calling convention or the signature. Did I miss anything here on unsafe extern? I feel like this is something you've probably used.
It's a little bit circuitous to kind of understand. I think so. Let's talk about like how you would do this before this feature existed. And so like the idea of let's say I have a C function, or let's say I have a Rust function that's just like internally uses some unsafe code. The idea being that I'm totally allowed to make it a safe function. I'm allowed to write fn foo. There's no unsafe there, so it's a safe function that doesn't require an unsafe block to call. Foo is allowed to internally use unsafe code to do whatever, and that means that I, as the author of the function, need to guarantee with my own eyes that this function doesn't have any sort of unsafe preconditions, that no matter what input or context in which the function might be called from safe Rust, it cannot violate memory unsafety. And this is totally possible. This is the point of Rust, is that we can encapsulate unsafe code in this way. So previously, if you had a Rust function that was calling a C function, and you, with your eyes, could have the ability to guarantee that no matter how this Rust function was called from safe Rust, it could never cause any kind of memory unsafety, even though I'm calling a C function. That's encapsulation. That happens all the time. But previously what you would do is you would declare an extern, some unsafe extern fn, some unsafe C function, then you would have a safe Rust function that just has an unsafe block inside, that calls the C function, and you have a comment on the unsafe block saying, hey, like, I've guaranteed that this is totally safe. And so now you just no longer need that sort of like intermediating shim function. Instead of having to write a safe Rust function that internally uses unsafe, you can just bypass that and say, hey, like, you still probably want to have, it's kind of like counterintuitive. The culture in Rust is that if you see an unsafe block, you should have a safety comment on it. Right. And so with these sort of like the safe keyword, which is now valid inside of this like, unsafe extern context, you probably also still want a safety block on that as well, even though
Yeah,
it
to
says
explain
safe rather than
why
unsafe.
is this safe to call beyond just the calling convention?
Yes, because it is still a safety assertion.
Yep.
You are asserting that it is safe to call this function, that no matter how this function is called from safe rust, it cannot cause memory unsafety. And if you get this wrong, it's memory unsafe. And so, like the safe keyword here is an assertion in the unsafe context of unsafe rust, because you have this unsafe keyword in here on the extern block itself.
And this actually relates nicely to the next bit that was added in 182 as well, which is unsafe attributes. So the observation here was that there are some attributes that are often used either in FFI context or in no-stud contexts that are actually kind of unsafe. Like an example of this being no mangle. So the no mangle attribute you can put on a function, and when Rust generates the like output assembly for linking, it will not change the name of that function, like the label it makes for that function in the resulting object file. And the reason you might want to do this is because you want it to be callable from other programs you're linking with or other libraries you're linking with. Like they assume that there's a label, there's a function by the given name, main being an example of this, right? So if you're writing an operating system from scratch, or you're writing like a native binary, there needs to be a label called main, which is the function that will sort of be the entry point for your binary. And that literally needs to be named main. Normally, Rust will sort of take the liberty here to generate a globally unique name for every function. And this is important because it means that you never can have two functions that end up with the same name in the final linked object. Now, if you put the no mangle attribute on a function, that no longer holds. So if you declare two functions, let's say in different modules, so they don't conflict in the Rust sense, and then you put no mangle on both of them, well, now they're going to conflict in the linking sense. And as a result, like now you have two labels but potentially different signatures, and this is just like ripe for undefined behavior very quickly. And so what they realized was some of these attributes really should themselves be unsafe. But before 182, there wasn't really a way to say that an attribute was unsafe. There wasn't really there was no place you could put the unsafe word. And so in 182, we got the unsafe keyword inside of attributes. So now no mangle and a couple of other attributes like link section and export name, which have similar problems, now need to be declared as, pound square bracket unsafe open parentheses no mangle, and then close the attribute. To specifically annotate that this is an unsafe attribute we're putting on this function. The old version, like without the unsafe, is still accepted, but it will be a hard error in 2024. And we'll get linting warnings for it in 2021 before that.
Yeah, and so I kind of want to like express, right? The way to think about unsafety in Rust, right? It's in theory, it's that safe Rust has no undefined behavior, totally memory unsafe. Obviously, in practice, bugs can happen in the compiler. Bugs can happen inside the
What?
library. Bugs can happen.
No.
It's true. No, it's true. Bugs can happen in any random code that you pull off the internet, right? Even if it's not malicious, it could just be mistaken. And so the idea of Rust is not that your code is memory safe, because that is kind of a difficult thing to guarantee. It is that if you didn't write the unsafe keyword, any memory safety isn't your fault. Or memory unsafety isn't your fault, right? And so that is the goal that Rust wants to uphold, right? And so like maybe it's a bug somewhere else, but like you shouldn't be the one to worry about this. But obviously, in these cases, there are subtle things. And so it's great that Rust exposes these things, because you might never think about, oh, I'm no mangling this thing. But like maybe I'm like, you say, okay, maybe in my crate, I'm using no mangle twice on the function with the same name. But what if you just use it once and then you accidentally link in to like, your like libc or whatever, and you just so happen to have like there's 10,000 functions in libc. You just so happen to name your function the same as some libc function. What happens? Well, I mean, in some linkers, they do like, have some pass that guarantees that there's no duplicate symbols. Some don't. And so because Rust cannot control what linker you use, this just has to be unsafe.
Yeah.
So
yeah, it's a good point that the conflict here doesn't even need to lie within Rust. It could be between Rust and something else.
Mm-hmm.
And And then we move on to non-unsafe land. This is more of an ergonomics improvement, which is you can now omit empty types in pattern matching. Do you have any use for this that you can think
Oh
of
yeah.
off the
Oh
top of your
no.
head?
So okay. No, there's this long saga, right, of the never type in Rust, and the joke about the never type
Yeah.
is the never type is self-describing in the sense of that's when it'll be stable,
Yep.
right? The never type is for those who don't know, haven't joined the saga, right? In like pre 1.0 Rust, the idea was okay. Let's say we have like some function and like it just like unconditionally panics. Like we have functions that do this, like so like standard OS exit or standard process exit, right? What is the return type of process exit? Well, it's not nothing. It's not like nil. It is guaranteed to never return. It just can't return. And so like what is the return type of this function? Like how do we type this and how do we integrate it with type system? And so there's a special case for functions like this where if you see like the return arrow and then exclamation point, that means it doesn't. Like so this function doesn't return in the type system sense. It just like it diverges to use the mathematical sort of nonsense jargon. With the idea
The
being that hey,
mathematical nonsense. You're gonna make
it
a
is.
lot of mathematicians very
Listen,
angry.
listen. I respect math. You're terrible at naming things, but a diverging function is a function that does not converge. It uh, goes off into space. It does whatever. It doesn't actually participate. Like if you draw the nice like diagram, the arrow points off into oblivion, right? You diverge, and so there is this kind of like if you want to write a function in Rust that diverges, that's totally supported and been supported. But the idea is how much of a type should this diverging return value be, right? Like in terms of like actually integrating. What if you want to store a value that is diverging? Or the what do we call this? And so the name for this is the never type, and that is never actually exists. And it's a fascinating topic because like it gets you like confront the idea of okay, we have this zero size type in nil, where like in information theory, the amount of like bits that you need to take up for a piece of information is like the log of the number of states in it, and because like the log of like state of 1 is 0, that number of bits for like a type of value 1 a type with one value is 0, and so nil, the empty tuple in Rust, is a zero size type, but it has a value. It has one value. You can't actually construct the value. And so what if you have a type with no variance? These are called uninhabited. And you can also easily make these. You just write enum foo, and then you give it no variance. And you can't ever actually construct a foo because there's no variance for it. You can't actually, it doesn't actually put any constructors into your scope. And so that's what infallible is. You see this kind of stood convert infallible. It's just a standardized sort of like, hey, like here's an enum with 0 variance. It's totally uninhabited. If you want to, say something can't ever actually be constructed like with this, you can use this. And so, what's the use of this? It's sort of like, in some sense, like right with because both this is a 0 size type. In theory, it's to say that the never type has 0 size is kind of like a sleight of hand. You can imagine if you wanted to be like again type system wonk, you could say, okay, actually stood mem size of should return an option where if you pass in the never type, it returns none. And if you pass it in anything else, it actually gives you a type, a number, right? But the idea here being, hey, what's the actual use? Like, why should we care about uninhabited types? Or like, what's the use? Like, what's it going to do for me? And this is actually the thing. And so this feature right here that gets stabilized is the super cool thing that never types allow you to do. It is the reason why we want it to be stable. And that's like that might actually be coming next year. But like, so the idea here
Wait, when
being
you
that
say next year, Ben, do you mean 2025 or 2026?
2026,
Okay.
it might be coming
So
next
in
year.
2 years, to be clear.
In 2 years from the date of this release,
Uh-huh.
of this these release notes. But the idea here being is that okay, let's say imagine for a second, right? So we have this idea of you write a generic interface, you have a trait, right, and it returns like some result, or you have a function that returns like result something tu, right? But what if someone implements this trait for their type, but they don't actually like this function just so happens it never actually fails. It's infallible. Like, and so in Rust we have this idea of both try and try from. So the into and the try into traits, where one of these is fallible and one of these is not. Why do we have two? Well, one can't fail and one can. But what if you have a generic sort of interface? How do you actually fulfill this? And so let's say that I implemented this trait for my type, which cannot fail. It can never actually return a result of error. Why should the consumer of this function be forced to handle a case that cannot happen? And so we would, in this case, use the never type to encode the idea that, hey, like compiler, I'm going to say that the error case for this is never, and then I'm going to not ever return uh, the error type from this, and you can check this for me. And so
It's
this
like
isn't an unsafe
statically
thing.
known that the error
Yes.
type is uninhabited and therefore cannot ever be chosen or
And
used.
then consumers of this function don't need to, in theory, what we're saying here is they don't need to check. And so when you do like say you have like a match foo where foo is a result, normally you'd have to say okay something, comma, error something. You have two arms. In the case of one of those arms being never, you only need the one arm. And so it goes from being, and then we have in Rust this idea between sort of like fallible pattern matching and infallible matching, right? Where if you have kind of like only one variant of something, it's infallible. It can never fail, right? There's only ever one actual way to do this. And so when you have a result where one of the fields is never, it means that you don't need to use a match. You can use a let statement. You can say let OK equals some returning result thing. And here in the future in Rust, we have like patterns for this for the cases that are fallible. You have like if let, you have let else, right? Where like, what if it is error? Like when you have to like handle that somehow in some branch. But with infallible types here, it means that you don't need that. You can just like you have like the ability to infallibly bind to the single like variant. So you'd see it let okay foo equals something and just carry on. And it's like, oh, it's so cool. It's so cool.
And
And that's what
I
this
think
thing is.
there's a really neat sort of synergy here to let else, right? Which is if you use let else, then the else block needs to diverge. The else block must not yield a value. Or rather, it must return in a sense. Exclamation mark. It must return never, because the idea is that the continuation of the function will be under the assumption that the let matched. And so the else cannot be allowed to feed into the rest of the function. It must, for example, return. And return has a value of never, which is its own little weird thing. But it means that the syntax here of let okx equals x if the error type is infallible is kind of similar to let OK x equals x else, and then the else branch is being inferred by the compiler because the else case is known statically to be never. It's not possible to reach. Yeah, well, 182 has a lot of these like really, I would argue like some of them are fairly deep improvements or changes
Oh yeah.
like to the language, because the next one here too is pretty substantial, which is the floating point nan semantics and const. So I think we've spoken briefly about floating point and nan in the past, but very basically, I'm going to skim over a lot of detail here. When you have a floating point number, there is one special state of floating point numbers called not a number. And what is special about not a number? Well, it's something that is not representable as a number. Like, for example, 0 divided by 0. But because of the way the floating point specification works, there are actually multiple such not a numbers. Like, not a number can be positive or negative. It can have a bunch of different bits in there that don't matter for the purposes of whether it's not a number or whether it's equal to other numbers. So there's a whole bunch of rules. Some of them are like actual rules in the standard, and some of them are just like whatever the hardware does for exactly what bits make up these not a numbers. This means that there are a bunch of floating point operations that are not really well defined. This is one of the reasons why floating point numbers don't implement ordering, is because not a number doesn't compares not equal to every other number and to itself, because two different not a numbers can be not equal to each other. So it's a partial order, not a total order. All of this makes it really complicated for us to implement floating point operations in const expressions, because the thing that you compute in the const expression might not match what the hardware will compute when you actually run the program. Because remember, const evaluates at compile time, which evaluates on your computer when you build the software, and that might be different hardware to where you're running the program. And so we've sort of been caught in this tricky position of figuring out, well, do they need to be the same? Should they at least be close to the same? Like, what should the semantics here be if we allow floating point in const? So what what the Rust language has now done in 182 is specify all of the different types of nans and how they behave. Now, there are parts of this specification, in air quotes, that are non-deterministic. So the spec will say things like the exact bits of a nan can be arbitrary as long as the nan bit is set, kind of. And so it's not an exhaustive reference. It's still, the idea is that this semantic specification still matches all known implementations of floating point numbers, but it doesn't dictate a specific one. And as a result, what they've been able to do is to say that floats in const in Rust follow all of those same rules. And those rules are expected to be followed by any hardware that you run Rust on. And there will be some things that you just cannot assume about that. Like if you take the actual bits of a floating point, they might not be identical between const and what you get on your hardware, but the semantics around nan will be the same. And that's sort of considered good enough for us to give floating point numbers in const, because you at least have written down rules about what you can and cannot rely on. And this has been like one of the big blockers to getting a lot of things into const, is that we haven't had floating point numbers, but now finally we will have them.
Right, and this is a very like subtle sort of thing. Like I had to go in and ask Ralph Young what the exact like sort of like details were about this, because like the idea of it's not deterministic is a crazy sort of like thing to think about. But to be clear, for any given Rust platform and like compiler version combo, it is always deterministic for that. And so like you're not going to compile your program twice and get different results. It's only when you change platforms or change compiler versions that some of these like nan representations are allowed to change. And so this is important because this is actually crucial for type safety, because of the way that constants can sort of flow into the type system. And so if this wasn't true, you would have like trivially achievable unsoundness via type unsafety. But
trivially achievable unsoundness sounds pretty bad.
Yeah. So, and the idea is that between compile time and runtime, some nan methods are allowed to return different results.
Yep.
If
crucially, like, different results between const and between what happens at runtime, but also between two different runtime executions on different hardware.
Sure, and at runtime executions, because some of these are in hardware undeterministic, which is just absolute first control. And so, but at compile time, it's always deterministic for a given compiler version and platform. Because it just has to be. And so if you change your compiler version, the results might change, and that it only applies to these specific nan methods or functions, right? Like about the representation of nans, like is it positive or whatever, right? And so it's not in general non-determinism. It's very tightly constrained. It is very carefully chosen to make it possible to do some floating point stuff, not all, because there are still some things that are just like totally wild that can never be done. If you actually hope to be sound.
And the blog post even gives us an example, which is if you take 0 divided by 0 and you call is sign positive on that returning nan, Rust does not guarantee whether that will return true or false. That's considered a non-deterministic operation on floats. So you cannot rely on that producing any particular sign, unless you are operating on specific hardware where you encode like on this hardware I can expect that the result is this. Constant seems to be a thing that sort of continued through in 182 as well, because we also now have constants as immediate values in assembly. This one I think is fairly quick to cover. So Rust has had assembly blocks for a while now, where you can write raw assembly code. And when you write raw assembly code, sometimes you have constants that you want to use as constant values in your assembly. Previously, there hasn't really been a way to do this because the assembly instructions you gave are basically, there's strings in Rust. There's a sequence of strings that are the assembly. And so you didn't really have a way to inject a constant in there, at least not in a convenient way. Whereas with 182, the ASM macro has now sort of learned about constants, such that you can, in your argument list to the assembly macro, you can say name of constant equals const name of constant, where the first name of constant is the name it will have inside of the assembly, so you can refer to it by that name. And the second instance of the name of the constant is the name of the constant from the context, like from the Rust program outside. And so this lets you propagate a const value from the Rust scope into the assembly scope, so that you can use them there rather than hard coding the value, for example. And then we have safely addressing unsafe statics. Is this something you've run into for work, for example, Ben, so far?
Well, not for work, but so the idea being in Rust. Okay, let's talk about this. Rust cares about making it possible. Rust's whole like raison d'être, right? You might think, oh, it's memory safety. No, wrong. Rust's whole reason for existing was to have safe concurrency, and it just so happens that having memory safety is required for safe concurrency because if you have memory safety, you don't have anything. And so, in order to solve the problem of how to have safe concurrency, Rust just, as kind of like a little aside, solved the problem of memory safety. But the whole point is that your Rust code fundamentally still cares about being concurrent. And so, all Rust programs, all safe Rust programs, must be reentrant. And that's just kind of like a thing, or it needs to exist, right? And Rust upholds at compile time. And one of the consequences of this is that if you have a global variable reachable from every thread, a static variable, mutating that requires some kind of synchronization, and that's up to you to provide, right? And so one of the consequences of this that wasn't really understood well for a long time was if you ever take a reference, a mutable reference, or I guess a reference at all, to a static mute, you need to guarantee manually that your code is reentrant, which is often almost impossible. And so it became unsafe. I forget if it was in this edition or previously. I think it was probably previous to this, to take a reference to a static mute, just because it was kind of like, hey, can you guarantee that your code actually here is reentrant? Probably not. And so you need to actually mark it unsafe to annotate that, hey, like what I'm doing here is probably nonsense. And you've always been required to use an unsafe block for actually mutating a static in Rust for this reason. All right, and so it's slowly over time, it's like gotten more strict. I'm not sure I remember what actually changed in this release. Something, I guess,
So I
some
think
pattern.
what changed is that now if you have a static mute, it is now it's safe to take a raw mute.
Oh, I see.
Now that we have raw as a
Yes.
way to get raw pointers directly, getting a raw mutable pointer to a static mutable is safe.
That's totally fine. Yeah, you're right. And so like I said, these sort of reentrancy properties about like you must not mutate through a shared reference, or you must have only one mutable references, obviously doesn't apply to raw pointers. Do whatever you want. And so now that we have this address, we don't want to say address. Raphael gets mad at you. This this pointer, this pointer operator. Pointer of operator, you can just do it like it's already like unsafe to use a raw pointer, and so this doesn't actually change the thing because it is not unlike in C where it is sometimes undefined behavior to even construct an invalid pointer, invalid raw pointer. It's only one kind. In C, in Rust, it's never undefined behavior to just construct an invalid raw pointer. You have to actually dereference it or to use it in some way.
Yeah, and even using it can be okay. It's like access is dereferencing it or casting it to something else that has invariance. That's the problem. Mm-hmm. But for example, like taking a pointer and then adding one to it is not inherently undefined behavior. Although something pointers that are too far out of bounds of their original allocation, so it's complicated. But there are things you can do to invalid pointers that are still valid operations on the pointer itself. Like it's not immediately undefined behavior.
Yeah.
I think that takes us to the stabilized APIs. So for the stabilized APIs for this one of the things, and the first one that's listed that I thought was interesting is spawn unchecked. I was actually surprised that we didn't have this previously. But spawn unchecked is a way to, it's a method on thread builder So you know how you have stood thread spawn? Well, so there's also stood thread builder, which lets you sort of configure thread you're about to spawn, such as giving it a name that many operating systems support displaying in things like top or the application info on macOS and such. And so you can create a builder and you can call spawn, and it's roughly equivalent to stood thread spawn, except with this additional configuration. Well, so now there's also a method called spawn unchecked. And the only difference between spawn unchecked and spawn is the spawn unchecked does not have a static bound. And so it allows you to, for example, take a reference that you have somewhere on the stack and move it into that thread that you spawn. This is normally, like, this is unsafe. This function is unsafe to call because you don't have a guarantee that that thread won't continue to run after the thread that created it and had that stack frame with the value the reference was pointing to goes away, returns, does something else. And so spawn unchecked is unsafe, but the idea is that by giving you access to it, you can now do things like for Rayon, for example, that wants to spawn a bunch of threads, and it guarantees that it will join them before the value goes away. For those kinds of operations, you can now use spawn unchecked sort of under the hood as the way that you construct threads. And I think before this, there was maybe a spawn unchecked on stood thread. No, there was none. So I don't actually know. I think what you had to do before was use raw pointers for this and move raw pointers across the thread boundary and then unsafely dereference them on the other side. Now you could just leave them as references, and it's the spawn unchecked called itself that becomes unsafe instead.
With regard to the library stuff, it's then kind of to point out some using the maybe an init type in stood, which is a way that you represent uninitialized data if you want to create something without paying the cost of initializing it to 0 first or to some other value first, create a thing piecemeal. It's now gotten easier to work with that for some of the composite smart pointer types like RC, ARC, and box. So there are now new underscore uninit methods, or I guess functions, constructors on these types, which make it just more convenient to work on these if you happen to ever use the intersection of maybe an init and any of these smart pointers.
And we also got a nice smattering of SIMD instructions that were stabilized, which is pretty nice in Core Arch. I don't think there was anything particularly special here, except I think more sort of features being made available. There's some cool stuff in later releases around some of these becoming safe to call in certain contexts, but in 182 is more just adding a bunch of these functions that weren't there before. And then I went through the detailed release notes here, and I think 182 is pretty good about outlining a lot of the items in the release notes themselves. But I did find one interesting bit, which is in 182, the binary search implementation in the standard library changed. So this improved binary search, not by a huge amount, although for some operations quite significantly. I think the improvement was like about 30% performance improvement for binary search, which is neat because binary search underpins things like B-tree map. There are also people who use it in their own implementations for various things, like if you implement your own quicksort, for example, then maybe you end up using some of this. Not quicksort. What am I talking about? If you had to implement like your own sorted data structure based on an insertion list, for example, then now calling the binary search in the standard library will be a decent amount faster, which I thought was neat. I think part of this was by making use of more branchless operations and conditional moves and stuff. I'll link the PR in the show notes for those who are interested. I think that's all I had for 182. Did you have anything else?
Nope, I'm good. Let's move on. Let's try and get one more done before I am dragged bodily
Amazing.
out of this recording booth. I might have to leave in the middle of it.
Is much more friendly sized than 182 was. Okay, so we're moving forward to Rust 183, released on November 28th, 2024. What's new in 183, Ben?
Right, and so the thing about sometimes features get stabilized, which unlock other features. Kind of like there's a flurry of activity, and so like these 82 and 83 are kind of like they were back-end improvements that allowed const to kind of evolve quickly. And so the new const stuff in this release, because of it was unblocked by decisions about like what's it mean to be deterministic, what are we allowed to actually do. There's a lot of new const stuff in terms of like both things becoming const. I believe I like scroll down. Um, yeah, there's like so many new stable const APIs. But the first thing here is new const capabilities. I need to remind myself what actually came in this release. Da, 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 da.
Yeah, so one thing at least is that consts can now have references. So you can operate with references in consts as long as it does not ultimately end up referencing a temporary. So it can end, like a const expression can evaluate to a reference to a static, for example, because that reference to the static is valid at runtime as well because the static exists. But
Right.
it can't evaluate, for example, to a reference to some value that you compute in the const because a const doesn't exist with the reference in a meaningful sense.
Right. This has always been allowed, right? For I believe like you could have like static strings have always been allowed in const because like Russ understands that hey, this like string literal is totally valid. I can just like paste this anywhere. So I believe the idea here is that this has been generalized, and so any static item you can now have a const whose value is a reference to that item's type and then refers to that item. Because the point of statics, the whole point of statics, the only reason you use them over a const is because statics have an address. They are guaranteed to have some kind of stable address, which is the whole point of a static. And so because it's not going away, you can just reference it. There's no problem. Yeah.
And you can also now use mutable references in const, which I think is a pretty big deal. Because the idea now is that in a const, you can take a mutable reference in and then mutate it, and then, that's all fine in const now. That was not previously the case. One of the things that this allows you to do is more easily write const helper functions, but it also lets you more easily write like turn fn's to be const fn's if they previously took mutable references. And so this sort of unlocks a whole subset of the space of functions that can now become const,
Okay.
where previously they couldn't just because they took a mutable reference.
Right. I was thinking about const values, right? And so const values have gained the ability to say, like, so the example here is const c colon ampersand I32 equals some static value. There's still not much reason to use allow const values to point to mutable statics to contain mutable references because like they'd have to point to mutable statics, which itself is kind of unsafe, as we mentioned previously, right? What you were talking about is about const functions,
Yeah.
allowing the parameters of that const function to be mutable references, which
Yeah,
is yes,
exactly.
fine.
And I think now there's also support for interior mutability in const expression. So you could, for example, have an unsafe cell inside of some a const expression you have. And again, I think this is an example of lifting a restriction that, like, there are a lot of places where you wouldn't use it, but it just means that more functions from the standard library that might use these things internally can now also themselves be made const. So we sort of float all of the fn stuff into const fn in the standard library.
Mm-hmm.
That's sort of the headline feature that was added in 183. I wasn't lying when I said 183 is a much smaller release. But there are a bunch of stabilized APIs beyond all of the, like, I think there's like, what, 50 constifications or something, maybe more in this version.
Mm-hmm.
But there are a lot of neat stabilized APIs as well. I think one that struck me in particular looking at this list was the error kind from std.io now has a lot more error kinds that are taken from various changes to operating systems and also an expanding set of operating systems. So things like file too large, host unreachable, network down, resource busy, all of those things previously would be surfaced as the other variant on error kind, whereas now they've actually been given a dedicated error kind that you can inspect for when you do various IO operations. And so this is just like expanding the richness of the API that you get to the operating system.
Right, and then people kind of like are not necessarily always pleased with standard I/O error because it's kind of like the most general interface possible for all possible platforms, and so it has to be sort of this somewhat low level, somewhat lacking very often. Mostly kind of like you want to like which file did I not find? Please tell me.
Yeah.
that
Yep.
kind of thing, right? But it is good to see it kind of like, getting some love there.
Another one I thought was interesting is option gained a new method called get or insert default, which I guess does what the method name says. So if you have a sum inside of the option, then it gives you a mutable reference to what's inside the option. Otherwise, it inserts the default value for the t of option t, and then it gives you a mutable reference to that. So it unconditionally returns a mutable reference to a t because after calling the function, the option will be sum and it will hold either the current value or the default value. And so this is another one of those that were like, it eliminates a trivial match that you would have to do otherwise. Kind of similar to in 182 where we talked about this thing about around the never type and infallible, where now you no longer have to match on them because the compiler knows. Well, this is a slightly different version where if your code is, well, just insert a thing if it's none, that no longer needs a match and can instead just use this helper function.
Hmm. Right. And as far as constification goes, again, there's so much here. There's stuff on duration, stuff on maybe on init, stuff on the non-null pointer type, once cell, option, result, ref cell, unsafe cell, arrays, chars, all sorts of float stuff, mem replace, pointer replace, all sorts of like, things on raw pointers and raw mutable pointers, things on slices, things on arrays, things on like stirs. It's wild. And again, because like, over time, these new const features allow us to constify more functions. And then when functions become const, it unlocks the ability to turn more new functions into const
Yep.
functions. And so, yeah, it's just, it's coming along.
I thought it was also entertaining to see. So the character type now has an associated type called min, or associated const rather called min, which is the minimum, the lowest valid code point a character can have, which is the null character. So it's the byte 0. I don't really know why this was needed, but Rust has had character max since 152, and character max is the highest valid code point in Unicode, which is like 10FFFF. And now I guess we also have min, which is just the null byte. And I guess it's for completeness,
If you're
maybe.
going to have a max, you got to have a min.
Yeah, exactly. Um,
So I
and,
don't know, just like to be consistent, I suppose.
And I guess speaking of, one of the things I realized was that in 183, when I was looking through the detailed release notes, we also upgraded to Unicode 16. And you know why that's exciting? It's because we
Mm.
get additional emojis. And so we get cool emojis like the fingerprint emoji, or the face with bags under eyes emoji, or the leafless tree emoji. But of course, the best one of them all is we now have the root vegetable emoji, because we didn't have that before, and now we are richer for it.
So here's the thing, though, is that because Rust, okay, as we mentioned before, kind of in passing, Rust, Unicode is lots of things. One of the things Unicode is sort of this like idea of determining a grapheme cluster and having operations for doing weird operations on Unicode values, which Rust does not support out of the box. You need to go get the grapheme cluster. What's it called? Grapheme something. Create. There's a bunch of crates for it.
Clusters?
Maybe I forget. But the idea is that like, why doesn't this like Rust supports Unicode, right? Why isn't this here by default? It's because the tables for Unicode has hundreds of thousands of characters, and the tables determining what operations are valid on what characters and what to return are like dozens of megabytes in size. Like they're huge, and so people would be the thought was before Rust 1.0, people might be up in arms if you just made every binary like 50 megs larger, because like they had like some Unicode support that like maybe they didn't use for whatever reason. You'd hope that these things would get optimized away. Who knows? But the idea here is that actually, in practice, so Unicode is allowed to make breaking changes because they do whatever the heck they want, right? Unicode 16 is allowed to, in theory, change things from prior versions, which remains true for all subsequent versions too. They obviously also are, have their own constraints about like what is and is not breakable in practice, but sometimes things do change. And so we kind of just need to deal with that, we meaning all languages which have Unicode support. But because Rust doesn't expose a lot of these operations, breaking changes in Unicode don't really make much difference. And so to your point about like new emojis, like because Rust doesn't have like any operations, as far as I understand, that really operate on like these sorts of things, it really shouldn't change anything. Like it's because you're mostly just like round tripping Unicode aware strings through Rust. Whether or not you're using a known or unknown emoji is irrelevant to Rust. It's not going to like suddenly be like, hey, I know what an emoji is. Um,
Yeah, whereas if Rust exposed a method like is emoji, or actually I
yes.
think emojis have a segment of their own, so you could probably check that without knowing the particular one. But if it had a
Mhm.
function like um,
Or like is assigned care point or something, right? Which would
yeah,
change
but
across
but
Unicode
you could
versions.
imagine a function like is a face emoji,
Hmm.
then you would need to know what all of the emojis with faces are, which might change with new Unicode versions. And so that one, might just return false for the bag under eyes one until Rust learns that that is important. But Rust doesn't have these, and so therefore it's not a problem.
Right. So, like, new Unicode versions are probably largely, unless they change like fundamental constants that Rust knows about, not necessarily like so. Languages like say Swift, which are much more Unicode aware out of the box, need to contend with these bricking changes. And like, you need to understand that hey, if you're using an older version, you might have like clients who are using your older version of the library, which expect something to happen, and then something different happens, and so you need to care about that. In Rust, we are kind of like insulated from that. But obviously, if you need to do it, you are using one of these crates, which themselves need to be aware of Unicode versions. And so, you know,
Yeah, so like if you, for example, had a crate that gave you constants for all the known emojis,
hmm
then that crate would need to change as a result of a Unicode bump because now there are new emoji names that would need to be expressed as new
you
constants.
make it sound like emojis are the only thing that happens with
They
Unicode
are.
releases.
What else is Unicode for? What are you talking about, Ben? Um, the
uh,
other thing I found, which I'm a little sad actually didn't make it into the release notes, was so in Rust 183 we got an implementation of RFC 3137, specifically a subset of it, which makes it so that when you have back traces in your Rust programs, those backtraces normally will, when it shows lines for code that's in the standard library, those will say like, or rather when you do it in your own programs, it will say, this function at, and then let's say main.rs colon 40 for line 40 of your main rs. If there's a function in the standard library, the at, like where it tells you where that thing was, the file name will be some weird path that starts with /rustc / some long hash / library / std / whatever. That path doesn't exist on your computer. That path comes from the debug symbols that were on the build host, produced by the build host that built the Rust C version you're using. But in 183, Rust learned to rewrite those, at least by default, you can turn this off. If Rust source is available, like the Rust up component Rust source, then Rust C will rewrite the paths in the backtraces such that instead of saying /rustc /hash, it will actually say the path to your local Rust source checkout for that file. And so now your backtraces, you can actually copy paste the path, open it in a program, and look at that file on that line, which I think is a really neat addition that I'm sad they didn't call out. And then I think the last one I had was a change. Oh no, I had a couple of others. Let's see. So for cargo, cargo, when you now run cargo update, cargo update will tell you about which updates it did not do because, for example, there's a newer major version, but your cargo toml says the previous version. So if you say cargo toml in your cargo toml like foo equals 1.1.3, and there's a release of foo 2, then it will tell you I updated to 1.2.4, but I did not update like latest colon 2.0.1. And so this way you'll be notified when your cargo update if you did not update to what is actually the latest version. I think by default, when you're in cargo update, it will just tell you that some things were not updated and you have to pass -- verbose to see the actual listing. But this is a real improvement for just being aware that even though you ran cargo update, you might not actually be up to date. Some of you will also be happy to learn that now when you run the command in cargo to like cargo build like dash dash timings that gives you like an interface that shows you how long cargo took to build your crate and its dependencies and do the linking and everything. The generated HTML report for that now supports dark mode, so some of you will become very happy in that it will not blind your eyes anymore. It will even switch automatically depending on your browser setting. Um, and then the last thing I dug up from the detailed release notes was a change in cargo nightly. So this one's not in cargo stable yet. I don't think it even is in 2025. But this is a change to how cargo computes whether a source file has changed or not. Currently, cargo does it based on the modification the modification time of the file. This is usually fine, but there are some file systems, especially like network file systems, that don't deal very well with this, because the modification time might just never been updated, or if you like do some remote syncs, the syncing tool might change the modification time. So a file might look like it's changed to cargo, but it hasn't actually, and then cargo will recompile a bunch of things unnecessarily. So there's work now in nightly cargo to make cargo use the hash of source files instead of the modification time, which when it eventually lands should give you fewer recompiles if you are on a file system or in a build environment where the modification times might not be entirely reliable. And that, I think, is all I had for 183. Do you have
Okay.
anything else for 183?
That's it. Let's try and do 184. 85 is a big release. Let's try and get 84 done. And if I get dragged out in the meantime, that'll happen. But let's
All
just
right, perfect.
keep on
All
going
right,
on.
Rust
January
184.
9th, 2025. The big thing in this one is Cargo considering Rust versions for dependency version selection. And so the idea being, I believe, is that so there's this idea in Rust of the MSRV, minimum supported Rust version, where if you are an author of a library, and let's say that you're like every single new Rust release, every 6 weeks or so, you listen to the podcast that comes out, like, oh, I got to update, and you got to use these new features. The problem is that if you're a library author and you publish a version of your crate that uses some new feature every single, like immediately as soon as every Rust release happens, then your users are required to update their Rust version. And maybe that's fine for you, maybe it's not. Many crates have sort of like voluntarily decided, like, say like Regex or whatever, right? Like, hey, like in order to not force users to upgrade every single time, we're going to have like some sort of slower schedule for understanding like what versions of Rust you will be required to use in order to use this version of this crate. And so this is called the MSRV. There is nowadays in modern Rust, there is a flag that a value that you can set in your cargo.toml that allows you to say, hey, I declare that any Rust version, this version or later, should be able to compile with this crate. And then it's often best practice to say, like in CI, actually test and make sure that's true to guarantee, because I don't believe this is actually enforced automatically. You require, like cargo doing much
It's
more magical
purely
things.
an annotation. Like it's not checked automatically, at least.
Mm-hmm. And I believe the change here is that cargo now gains the ability to, now that it's we've been like several like years out from crates having this feature. Now that ironically the flag indicating what version of Rust you compile against is now old enough to be in crates that actually care about having long-term support for older compilers. Now Cargo is aware of this and can try to select, if you are on an older version of Rust, try to resolve dependencies in a way that will actually work for your version of Rust.
And crucially, what this means is when you run, for example, cargo update, you might not be updated to the latest version of a dependency because your Rust it doesn't support your Rust version. Like the latest version doesn't support your Rust version, and so cargo might hold back that version update and only update to the latest one that actually works with your compiler. And this ties into the feature from 183 where cargo update will now tell you about cases where it hasn't fully updated. And so you can run cargo update -- verbose to see the places where you are still behind.
Yeah, and one of the reasons this matters is that because it's kind of been like a long discussion in the Rust community of like, okay, like should it be a breaking change in terms of like I have a library, should I bump the major release number if I update the MSRV? Because in theory, it could break someone who's like using it, because the way that Cargo works before this is if it sees a new major or a new compatible version, it'll just update it. But if I'm using an old version of Rust, an older version, it could cause my builds to stop working. And so the idea here is that this, the conclusion, despite this, kind of the consensus among many people, which is that yes, it's a minor change. It's minor, it's not breaking. It's just like you just need to update occasionally, which has both good and upsides and downsides. But hopefully with this, it should resolve that, because now if you are on an older version, it shouldn't be. It should, in theory, assuming that there exists some possible conclusion to your dependency resolution for your version, it should just continue keep working.
Yeah, although you do still bear the burden that if you run an old Rust version, you might end up building old versions of dependencies because that the newer ones don't support you. And as a result, that could mean that you're running with, for example, known security vulnerabilities in your dependencies. So like this does not release you from the responsibilities of keeping your Rust version up to date. But it does mean that if you're forced to use an older version for some period of time, should have a slightly less bad time doing so.
It also, in theory, requires every crate in your graph to declare an older Rust version, because maybe if they don't declare the version and they do update the thing, then it'll break you regardless, because Cargo has no idea what it means to, so.
The next one here is the migration to the new trait solver. This is something I think we've heard something about for, I feel like, close to 10 years. Maybe not, maybe like 5 or 6 years, certainly. And this sounds like it's the first time when the new trait solver is actually being used for something that's stable in the language. Do you have more knowledge about like the exact thing they implemented here and
so
where we're going next?
The way that you describe Rust or any large project of like, trying to be stable, but also trying to like overhaul large features, is that you're trying to like rebuild a jet engine while the plane's in flight. You've heard about like the trait resolver being written for many years now, because the idea is that there are some known limitations that block new features we want to have, or just like lots of correctness fixes we want to have in there. So like, there are soundness bugs. But I think the most current, like oldest and most famous soundness bug is related to trait is currently blocked on this new trait resolver. I'm not sure if it's necessarily going to be solved by merely adopting it, but like traits are a pretty big thing in Rust. It's probably like one of the biggest in terms of like most complex, most
and most novel
load-bearing
in a way too, right? Like
yeah, in some ways. But in terms of like of the language, lots of things rely on traits working properly in terms of like just generics and operator overloading and all this stuff, virtual dispatch, right? One, you need to add new features in ways that we know works. Two, don't break anything. And three, don't regress performance. Doing all of these turns out to be pretty hard. And so we should just like do an interview sometime with like Jack Huey. He's here in town. I can just like talk to him sometime. Love to get his like insight into like, well, what does it mean to have a new trait solver? Because it should be largely transparent for most people. Most people should kind of like upgrade your compiler. It's either gotten faster or hasn't at least gotten slower. And maybe they've have some new fancy feature that they can use directly, or they can have new crates that benefit from the new fancy feature.
And it looks like in 184 that they specifically only started using it for checking the coherence of trait impulse. So it should only deal with like the whether you're allowed to implement this trait in this crate or not.
Yeah, so the trait resolver does lots of things, and so the new trait resolver is kind of just like, hey, like we are now turning on for one of the trait resolution responsibilities, we are just for this pass, we are turning on the new features to kind of like flesh it out and like kick the tires some. And so in theory, more will be turned on over time for this, which will eventually unlock lots of new stuff. But yeah, there's a whole blog post for this, and we should just link to that in the release notes.
And then I think the last bit in 184 is the strict provenance APIs. And this ties into the discussion we had previously about what is a pointer, and is a pointer the same as an address? And the answer that the Rust community has stabilized on is no, they are not the same. There are additional rules for what makes a pointer beyond simply the address that it contains. There's a great sequence of blog posts here by Ralph Jung. I'll link them in the show notes as well. Highly recommend reading also the RFC 3559, which is the one that is simply titled Rust Has Provenance, where provenance is the difference between an address and a pointer. So a pointer is address plus provenance, roughly. And so the, with the acknowledgement that Rust has provenance and that there's a distinction between these two, comes the need to provide mechanisms in the standard library for adding provenance to an address or taking provenance away from a pointer to turn it into an address. And these are what are known as the strict provenance APIs. This is a sort of group of APIs that are added to the standard library that specifically talk about this concept of provenance, like which allocation or which object did a pointer originate for? Like which one is it pointing to, regardless of whether its address is currently pointing out that object? Which one does it sort of stem from? And we won't get too much deep into like the details of exactly what provenance is and how it works. Maybe for that we should have a chat to Ralph at some point.
We have in the past gone over it in great detail, and we should for the moment just say, hey, Arya being Esner Gangara has a really good long blog post on this topic that we should link people to. Arya also wrote most of the documentation, also designed the strict provenance APIs for these things. And so we can maybe in the future, if it would be nice to go over this and talk about them more in depth, not that they've been stabilized, but I don't think they've changed since we last talked about these being added in the first place.
I mean, to summarize them briefly, right? So the idea is that you have on the pointer types, you now have a method called adder that gives you the address of a pointer. You also have a method on a constructor on pointers that lets you take an address and turn it into a pointer, and then it documents which provenance the resulting pointer will pick up and add to the address. You can also construct a pointer by taking a pointer you already have and an address and say, I want to create a pointer that has the provenance of the pointer I already have, and the address of the address I'm pointing in, that's now going to be the new pointer. So sort of ways to actually deal with the concept of provenance directly in the library.
Yeah, I think we're kind of being very high level here. I think at the low level, like, rubber meets the road idea. The point is that for a long time, we treated pointers like they were addresses, where we, as in like language designers and language users, compiler authors, in terms of like writing optimizations, accidentally, as this emergent property of wanting to write code that optimizes well, kind of like accidentally invented this idea of provenance without even realizing it. It's an emergent property of compiler optimizations. And hey, actually, it turns out if you want really good optimizations, you need to consider this sort of like hidden compile time only property, this information associated with pointers that we kind of associated kind of like implicitly. We didn't realize we were doing it. It's
it basically means that the compiler and the optimization passes can assume more things about your pointers and therefore optimize their use better.
Yeah. And so the point is that if you are round tripping, if you have a pointer and you are going from pointer to integer to pointer, then you need to care about this. If you're just going pointer to integer, that's fine. The problem is going from integer to pointer, because then you need to understand, okay, well, there is missing data here, and that missing data is the provenance. Where does it come from? And so this idea of strict provenance is kind of like trying to grab the entire like culture of programmers using pointers and say, no, this way. You need to think about this one operation if you want your optimizing compiler to, one, be correct and not memory unsafe, and two, actually do its job well and be fast. So.
And actually, if you look back at past Rust releases, you'll see a clue to this, which you'll see that many of the pointer types, especially the atomic pointer type, has gained operations that allow you to do like bitwise not or bitwise or, bitwise add. And the reason for this is because you want those operations to be done directly on the pointer to indicate that you are preserving the provenance, rather than forcing them to be stored as an atomic usize, which doesn't have provenance. So you need them to actually be pointers where the operation happens on the address of the pointer without changing the provenance. Yeah. So there's sort of the markers have been put down. There's some breadcrumbs along the road there.
And in particular, one of the kind of like escape hatches you can use for this, there are ways to totally escape strict provenance. In that case, it's kind of unclear how we would ever specify the behavior in terms of like standardizing a safe subset of undefined, unsafe features. But if you do need to do wacky stuff with pointers, the strict provenance APIs provide this sort of like map adder with adder thing where it lets you like kind of you give it a closure where you do your wacky stuff, and at the end of the closure, Rust automatically gives you back the provenance you had before you did the stuff. And so you can like do crazy stuff with like stuffing values into pointer bits to store like stuff in the unused upper bits.
Yeah,
of
which
a pointer.
A lot of like concurrent libraries end up using.
That's still fine with provenance. You just need to make sure you use these
Yep.
methods to regain the provenance you once had automatically. I believe they're even safe.
Yep.
So
Yeah,
yeah.
they are.
And so in terms of like, yeah, go on.
No, I was gonna say, in terms of stabilized APIs,
Yeah.
there are a couple of other tiny ones. Like one of them I noticed is you can now take the square root of integers, or the root of integers, which previously you could only do on
Oh, yes,
F64s.
those are on ints. Yeah.
Which I thought was a neat addition.
Rounded down. So
Yeah.
I assume that. Okay. Yeah. Rounded down is fine. There's no negative square root. Okay.
And the other one I thought was neat was that on core pointer, there's now a dangling constructor, which creates a pointer that is not null and that points to no valid allocation. Or rather, it doesn't guarantee anything about where it points, except that it doesn't point at null. It is specifically intended to be used as a dangling pointer. And this ends up being used in vectors. So when you create a new empty vector, Rust uses the pointer to the vector points at nothing when the length is 0, where the capacity is 0. But the pointer being null is used as a niche for if you have an option vector. So they can't make that pointer be null. It has to be some other value that's not null, but is also not going to be used. And so that's what you now have the pointer dangling constructor for. That just returns you some pointer that's not null, which I thought was neat. In the detailed release notes, the main thing I found was that cargo will now include cargo lock in all published crates. So when you run cargo package or cargo publish and you produce a crate file, previously that would only include the cargo lock for binaries, for binary crates. Now it will include the cargo lock for all crates. And I think part of the intention here is to make things like crater runs easier, because now when you download a published crate, you know exactly which version of dependencies it was using at the time, which you wouldn't otherwise necessarily know for a library crate, because the cargo lock wouldn't be in there, or you have this cargo toml, so you might have to pick the latest version of all the dependencies, but that might not build with a current version of Rust, and so it becomes this really annoying thing to try to figure out. Whereas if you now bundle the cargo lock and everything, then that problem goes away. The other thing I noticed was that in the compatibility notes for 184, they note that the WASM32 WASI target name has now been removed. The target is now named WASM32 WASI P1. Just like the transition plan that we originally led at the beginning of this episode on Rust 181 was the plan all along. So that finally took effect now in 184. And I think that's all I had from the detailed release notes. Do you have anything else for 184?
That's all just in there, kind of like we were talking about how the trait resolver, the new trait resolver, kind of like it. The idea is to eventually begin fixing these soundness bugs. Actually, apparently using it for coherent checking alone already fixes a number of soundness bugs. And so benefits there. Again, we should just interview Jack Huey sometime and like have him talk at length about, trait resolution. I'm sure it'll be a fascinating topic that people will love to tune into. So
Oh, there's one last one actually that I thought was kind of interesting on this topic of raw pointers we talked about. It turns out that one of the things that is also that they discovered was okay is, imagine you have a some pointer that's to an invalid location. You put a star in front of it, and then you put ampersand raw in front of that. So you have ampersand raw star invalid pointer. This is also valid. This is safe. It's not undefined behavior, because even though there's a star there, that star just refers to the place of the target of the pointer, but it does not actually dereference the pointer. It only does so if you use it in an expression context. But if you use ampersand raw star, then you're not using it as an expression context, you're using it in place context. And so it just resolves to the same invalid pointer. So you still end up with an invalid pointer, but there's no undefined behavior in between. And this, they only realized in 184. So before 184, that kind of expression was disallowed because it was considered being dereferencing an invalid pointer, but they were like, actually, this is fine. There's no problem here.
Okay, is that it for our 1.84?
I think so. At least I don't have anything else, which means we made it through all of 2024, Ben. We're now
done.
up to 2025.
In the current year. It is
It's
current
amazing.
year.
It feels good. It feels good.
It's great.
So I guess this means we're gonna do another extravaganza, mega, super long extreme
Yes, I'll
stream.
try and get the booth for more than 2 hours next time, and we'll finish all the rest. Okay.
Yeah, I mean, we're pretty far along the way, right? 190 is the latest one, so we just have like 6 releases to get through. We can do that in an afternoon. Should be no problem.
We're averaging half an hour per release at this rate, so
Yeah.
we're doing pretty good.
I think it'll be great.
All
Cool.
right.
Thank
gotta
you,
get outta
everyone.
here.
Thanks for coming.
See ya,
I
folks.
hope you had fun, and these will also come as podcast episodes. Cool.
Bye-bye.
See ya. Bye.